Okay, this section, section 3.2, is going to cover rational functions, okay? And we are going to talk really all about vertical, horizontal, and asymptotes within this section, okay? So, I want to start off by making sure that you remember a couple of formulas here. First of all, if we were going to factor a cubic, the difference of two cubes, or the sum of two cubes, okay? If I have x cubed plus a cubed, this would factor into the cubed root of x is x. So anywhere, so the first thing you do is you take the cubed root of x and you replace all these x's in here with the cubed root of x, and you do the same thing for a. The cubed root of a, and we come in here and we replace a each time with whatever the cubed root of a was. So these are two formulas that you might have not remembered. And I also want to remind you of the formula for a line, y equals mx plus b, where m would be the slope and b would be the intercept of the y-axis. Okay. Having said that, we want to talk about a rational function. Now, rational functions are in the form of basically a fraction, where I have some polynomial function in the top and some polynomial function in the denominator, okay? And the only catch here is that, don't forget, we cannot let the denominator be equal to 0, okay? So we start off our discussion about asymptotes with vertical asymptotes, okay? Now, remember that if I have a function like this, I really am concerned where the denominator is equal to 0. So what we want to make sure that we have, first of all, is that my rational function first needs to be in its lowest terms. Okay, so whatever our function is, our fraction, we want to reduce it and put it in its lowest terms. And once it's in its lowest terms, we then want to determine where the denominator, q of x, would be equal to 0. Okay, that's what we're finding. And this is going to give us, remember, a vertical asymptote is going to be a vertical, we draw it like a dotted line, but it's where our graphs might approach this dotted line but never touch it. Anytime we have a vertical line like this, the equation of a vertical line is always given as x equals something. In other words, if this is a, where it crosses the x-axis, then we say that the equation of that line would be x equals a. Okay, so we needed to have that kind of background information to be able to find the vertical asymptote of our functions. So this first example says, okay, find the vertical asymptote, if there is any, of this graph. I'm looking at this function, f of x, which is equal to x plus 3 over x minus 1. And I can see that the numerator and that this function is already reduced. Now, don't be fooled into thinking that I can just reduce these x's like that, because I can't. That's a huge mistake and a big no-no. If my numerator has an addition or a subtraction sign in it, then my order of operations are going to tell me that I have to perform that addition or subtraction before I can ever do the fraction bar, which is division. So just kind of a warning, don't try to reduce this if there's an addition or a subtraction sign. Now, since my function f of x is already reduced, then all I really need to do is determine where the denominator, x minus y, is equal to 0. When I set that equal to 0, I can quickly see that the equation of the vertex, the equation of the vertical asymptote, occurs at x is equal to 1. Okay, so this is important. This is the equation of the vertical asymptote. And that's it. That's your answer. That's all it was asking for. All right, let's try that again. Let's come over here and let's look at this function. R of x is equal to x over x squared minus 4. I can't just reduce it like this. I have to put my denominator as the product of factors. In other words, I got to factor the denominator. So x over x plus 2 times x minus 2. Remember, this is the difference of two squares. It always factors into this. I can see that there are no factors that I have in common that I can reduce. So instead, I'm going to go ahead and determine where my denominator, which I'm going to look at it as this, where is my denominator equal to 0? So I come and I set each one of these, x plus 2 equals 0, x minus 2 equals 0, and I see that x is equal to 0 at negative 2, x is equal to 0 at positive 2. So the graph of this would have two vertical asymptotes, each one occurring at negative 2 and positive 2. Okay, so this is your answer. Make sure that you're giving your answers as the equation of the vertical line. The next example we're going to look at is h of x is equal to x squared over x squared plus 1. Okay, and we're trying to determine where the denominator is equal to 0. That's what we want to be asking ourselves. Where does the denominator equal 0? If I take a number and square it, I'm always going to have a positive number. And if I add 1 to a positive number, I'm always going to get something greater than 0. Okay? So let's just take at random some negative number and we'll plug it in. I don't know, let's choose negative 5. Negative 5 squared plus 1 is going to give me back positive 25 plus 1, which would be 26. Okay, so that's not 0. Let's pick another value just to test it. What if I picked negative 1 and squared it plus 1? Well, negative 1 squared is 1 plus 1. That's going to give me back 2. And then if I choose positive values, let's just choose, I don't know, positive 3. 3 squared plus 1 would be 10. The point I'm trying to make is this denominator will never be equal to 0 because I'm squaring whatever my value is and then adding 1 to it. I can never come up with 0. So since it will never be equal to 0, there is no vertical asymptote. Okay? Okay, and finally for the vertical asymptotes, we want to talk about this one. X squared minus 9 in the numerator over x squared plus 4x minus 21 in the denominator. Now I can tell you right now that this whole rational function is definitely going to factor. So we're going to factor this into the difference is squares in the numerator, x minus 3, x plus 3. In the denominator, I'm going to factor using trial and error. I know this factors into two binomials. My first term is going to be an x and an x. Because this is a minus sign, I'm going to have a plus and a minus. I have opposite signs. I also know that I'm looking for the factors of 21 that subtract to give me 4. The factors of 21 that subtract to give me a positive 4. Well, that can only be a positive 7 and a negative 3. Plus 7x minus 3x gives me back the 4x that I needed. Now that I have the numerator and the denominator factored, I want to see about canceling any factors out. Well, I have an x minus 3 down here and an x minus 3 up there. So I have reduced my my rational function to be x over 3, x plus 3 over x plus 7. It is this denominator of factor of x plus 7 that I want to say, okay, well, where does that equal 0? That equals 0 at negative 7, which is the equation of the vertical asymptote. Vertical asymptote, okay, which is what I was asked to find. One thing I want to point out, though, is remember that x minus 3 that we canceled off? It ends up being just a hole in the graph. And I believe that the function, when I graph it, looks something like, I know I have a vertical asymptote over here at x equals negative 7. And if I remember right, I think it graphs something like this and then this. But because I cannot have a 3 in the denominator, as is clear from this factor here, what happens is I have an open hole right there in the graph. It just caused me to have a hole in the graph. Remember that this number, x minus 3, at 3 is part of the domain of this function. Okay, so I cannot have a 3 in the denominator, but I can have x is equal to -7 for a vertical asymptote. Okay, that's what you do when you find vertical asymptotes. You're basically just looking for where the denominator is equal to 0 after you have reduced your rational function. Now I want to talk to you a little bit about horizontal or oblique asymptotes. Okay, horizontal asymptotes would have the equation of y equals something because they're a straight line going this way. Oblique asymptotes are really just a line that has an angle. It's just a line that might look like this, okay? That would be an oblique. Now we have two possibilities here for our asymptotes of rational functions. And I want you to understand that if the degree of the numerator is less than the degree of the denominator, we end up with a horizontal asymptote at y equals 0. Okay? That's kind of one first choice. The second choice says if the degree of the numerator is greater than or equal to the degree of the denominator, we have to use long division to find out what the horizontal or oblique asymptotes are going to be. So let's practice that, and I can describe what I'm talking about a little bit further. This first example says find the horizontal asymptote if one exists of this function. Okay, I don't have to worry about reducing this function, but instead what I'm concerned with is the degree of the numerator and the degree of the denominator. When we talk about the degree of a polynomial, we look at the leading variable. Most of these are always written in descending order with our leading variable the highest number, right? So I start here, I'm going to look down here. I start with x squared, then I move to x to the first, and finally to the 1. So you can see that this is written in descending order, and in order to determine the degree of the numerator or the denominator, or the degree of my polynomial, all I do is look at this leading variable. In the numerator, this is raised to the first power, so we say that it has this polynomial is of degree 1. And then in the denominator, this leading variable x squared, or x, is raised to the second power, so it is of degree 2. So in order to evaluate this and figure out which one of these rules this applies to, the degree of my numerator is 1, which is less than the degree of my denominator, 2, and therefore this is pretty easy. The horizontal asymptote occurs at y equals 0. And that's it. So now that you know how to find the degree of the polynomial, you can start to figure out which plan A, plan B, choice 1, choice 2 we're going to use. So that's it. Horizontal asymptote occurring at y is equal to 0. Remember that horizontal lines will always have the equation y equals something, like y equals a constant. So let's look at this example here. This says find the horizontal or oblique asymptote if one exists. The very first thing that we need to do is determine what the degree is of my polynomial. The numerator has a degree of 4. The denominator has a degree of 3. Okay? So since the numerator is greater than the denominator, then I know that I'm going to have to use long division. So I have to use long division to determine what my horizontal or oblique asymptote is. So this is going to take us back to something you probably haven't used in a while, but remember that if I do long division, which is what this fraction really can be broken down into, I take the numerator right here and I stick it underneath the house. So I have 3x to the 4th minus x squared. And then on the outside I put the denominator, x cubed minus x squared plus 1. Now I just generally have the habit of filling in my spaces where I'm missing here. Notice that I have an x to the fourth and then I skip to an x squared. So what happened to the x to the third? I'm going to put that minus sign next to the x squared. What happened to my x to the third term? Well, it's not there, but we are going to write it in my long division under the house here just so that it can hold the place of the x to the third value while I do my long division. Okay? So, now I'm ready to do the division, and the way that I approach this is I always look at the first term here and the first term on the outside, and I decide what is 3x to the fourth divided by x cubed. Well, that's 3x. So this 3x is what I put here in the first position. Now I'm going to multiply what's on the top here by each one of these three terms on the outside. So 3x times x cubed gives me 3x to the fourth. 3x times negative x squared is a negative 3x cubed. See how that fell right into that spot? And 3x times a 1 is going to give me, I'm going to scoot over here and I get a 3x, right? 3x times 1 is a 3x. So really, I'm also missing the x place value as well. One thing you have to make sure that you do when you do long division is now I have to subtract this polynomial from the one above it. And when I do that, that has the effect of changing all of these signs to the opposite. And now I can add straight down. So this first term disappears, and if it doesn't disappear, then you didn't do something right. You need to go back and check. The second term becomes 3x cubed. Let's bring our minus x squared down, and then negative 3x. Okay, so I start the process all over again. I look at this first term, 3x cubed, and the first term on the outside, and I say, what's 3x cubed divided by x cubed? That would be 3. So I put that plus 3 up here. And I multiply this 3 times each one of these three terms. So 3 times 3x cubed would be 3x cubed. 3 times a negative x squared is a negative 3x squared. And 3 times 3 would be a positive 3. Because I can't put that underneath this x since it is not a like term. Now remember, the next step would be to change all of these signs and then add straight down. The first term disappeared. The second term becomes a 2x squared minus 3x minus 3. Okay, this is where I stop. This right here is the remainder. I know that because this x squared is less than x cubed. So I know that when this term is less than what I started with on the outside, that this is my remainder. And the only thing that I am interested in after all of this long division is this part up here that's left. That turns out to be the oblique asymptote. It looks a whole lot like a linear equation, and that's what it is. So I write this as y is equal to 3x plus 3. And that would be the diagonal line that would be my asymptote. So this is the equation of my diagonal line. So what that means is when you use long division, you do the long division process, you stop when you get to the remainder and you ignore it, and you're only interested in the linear part of your answer. Okay, so this is my answer right there. That was the oblique asymptote. All right, let's try again. Here I have the rational function 8x squared given up top, 4x squared on the bottom. The first thing I want to do is determine the degrees, remember? This is a second degree polynomial. This is a second degree polynomial. Those are actually equal. Anytime the degrees are equal, we are only going to be interested in their coefficients. So I'm going to rewrite this as 8 over 4, which is actually 2, and that becomes my equation for my horizontal asymptote. We just take the 2, we rewrite it as y is equal to 2, and that's how I get the horizontal asymptote. Now I can do long division on this problem, and I am going to do it for you just so you see that that's what happens. But you don't have to do long division on this. All you have to do is determine what the degrees are. If they're equal, you use their coefficients to find out what the y equals line is. But I'm going to show you the long division because I think I must like practicing it. 4x squared minus 1 goes into 8x squared minus x plus 2. We start by these first two terms. So I think, what is 8? What is 8x squared over divided by 4x squared? Well, that's 2. So I multiply 2 times 4x squared, and I get 8x squared. 2 times a negative 1 gives me a negative 2. We have to line our like terms up. Remember, we have to go through and change our signs. The first term disappeared, so I bring down my x. I get negative x plus 0. Oh, sorry, plus 4. Now, this x is less than the x squared on the outside, so I know that this would be the remainder, which is what I'm going to ignore. Okay, that's the remainder. And what I'm left with is the number 2, and that happens to be the answer that we got by just looking at the coefficients to begin with. Okay? So you can do long division on that if you really want to, but you don't have to. Now let's look at one more example. The last example I have here is this rational function. Okay? And we want to determine what the degrees are here. So the degree of the first polynomial is a 5th degree, 5. The degree of the denominator would be 3, and I know that 5 is greater than 3. So I must use long division. Okay, so we take the denominator x cubed minus 1. We have the numerator underneath as 2x to the 5th. I'm going to fill in my places. Plus 0x to the 4th minus x cubed plus 0x squared plus 0x, because that's what I'm missing, plus 2. Okay? And now I decide, I look at my first term here and the first term on the outside. So 2x to the 5th divided by x cubed is actually 2x squared. And that's what goes right here. 2x squared. Okay, so 2x squared times x cubed is 2x to the 5th. 2x squared times a negative 1 would be negative 2x squared. Okay, so I had to line up my like terms. Now let's make sure that we change our signs and add straight down. First term disappears. I don't need to worry about the 0x to the 4th, but I do need to bring down my negative x cubed plus 2x squared. So we look at this first term, negative x cubed, and this first term. So I have a negative x cubed over or divided by x cubed, and I get negative 1, which is what we write right there. Negative 1 times x cubed is negative x cubed. Negative 1 times a positive 1 would be positive 1. I mean, negative 1 times a negative 1 is a positive 1. Okay? Make sure that we change our signs, and then let's add straight down. The x cubes disappear. I get 2x squared. I don't have to worry about the 0x, but I do have to bring that 2 down. So plus 2 minus 1 would be plus 1. Okay, so this x squared is less than this x cubed, so this is the remainder, and I don't care anything about it. But I want to come back and look at what is left. Notice that this part that is here that's left is actually something is raised to the second power. This is not a linear function anymore. This would be considered a quadratic function. Well, I'm only interested in linear functions, so since y would be equal to 2x squared minus 1 is not linear, then there is no horizontal or oblique asymptotes. Okay? Because this number right here, or because that equation that we found is not linear, there aren't any horizontal or vertical asymptotes. Okay, now I want to kind of go back and summarize something for us really fast. Okay, so I'm going to go back up here. Remember this problem we worked just a few minutes ago where I said if the degrees of the numerator and the denominator were equal, then we use the leading coefficients to find out what the horizontal asymptote is. So I want to just write that down. If the degree of the numerator is equal to the degree of the denominator, then the leading coefficient gives us coefficients give the equation of the horizontal line, like we saw in that example above. And then I want to summarize this one down here because there is kind of a generalization that you can get out of this. Okay, the generalization that I want to come up with on this one is if the degree, let me write this over here. If the degree of the numerator is equal to, and let me state it like what's on your cheat sheet that I have, just a second. Okay, this summary that I was thinking of is actually coming out of your book, and it's stated really well in there for this generalization. If the degree of the numerator is greater than or equal to twice or 2 more than the degree of the denominator, so the degree of the denominator plus 2. Okay, like we had over here. Okay, the degree of the numerator was twice, or the degree of the numerator was 2 more than the denominator. That's what I'm wanting to say. The degree of the numerator is 2 more than the degree of the denominator, then there will be no horizontal or oblique. Then no horizontal or oblique asymptotes. You can always find these out by doing the long division, but just so that you know that that generalization is there. Okay, so we had quite a few different options once we were determining the degree of the polynomial, the degree of the numerator versus that of the denominator. And these are the examples that cover that. Okay?